Pioneer anomaly. You're an engineer at NASA's Jet Propulsion Laboratory. The year is 1980. Pioneer 10 and Pioneer 11, twin spacecraft launched in 1972 and 1973, are cruising past the orbit of Saturn, heading for the outer solar system and eventually interstellar space. They've completed their primary missions. They've sent back the first close-up images of Jupiter and Saturn. Now they're coasting, drifting outward on trajectories calculated down to the meter using Newtonian mechanics and general relativity. The math is settled. You know exactly where these spacecraft should be. Except they aren't there. Both Pioneers are drifting off course. Not randomly, not in different directions. Both are decelerating slightly as if something is pulling them back toward the sun. The force is tiny, about 10 billion times weaker than Earth's gravity, but it's persistent. It's consistent across both spacecraft, and it doesn't match any known force in physics. The anomaly was first noticed in the early 1980s by John Anderson and his team at JPL. They spent years ruling out the obvious: fuel leaks, solar wind pressure, magnetic fields, gravitational influences from known objects. Nothing accounted for the drift. By 1998, Anderson published a detailed analysis in Physical Review Letters confirming the anomaly. Both Pioneer 10 and Pioneer 11 were experiencing an unexplained sunward acceleration of approximately 8.74 times 10 to the negative 10 meters per second squared. Constant, unchanging, present in data spanning over a decade of tracking. The number mattered because it was suspiciously close to a fundamental cosmological value. The anomalous acceleration was approximately equal to the speed of light multiplied by the Hubble constant, the rate at which the universe is expanding. This numerical coincidence sent a shockwave through theoretical physics. Was the Pioneer anomaly evidence that gravity behaves differently at large distances? Was Newtonian mechanics breaking down at the edges of our solar system? Some physicists proposed modifications to general relativity. Others suggested the anomaly was the first observational evidence of dark energy acting on local scales. Mon theorists. So proponents of modified Newtonian dynamics who argued that dark matter doesn't exist and gravity itself changes at low accelerations saw vindication. Papers multiplied. Conferences were organized. The Pioneer anomaly became one of the most discussed problems in fundamental physics. Then in 2012, a team led by Slava Turishev at JPL published a comprehensive thermal analysis. By reconstructing the spacecraft's design specifications and modeling the heat radiating from their onboard plutonium power sources, they concluded the anomalous acceleration was caused by thermal radiation pressure. The plutonium generators emitted heat asymmetrically, with slightly more infrared radiation pushing backward than forward. The case was declared closed. The Pioneer anomaly was just heat. Physics was safe. But the thermal explanation has never satisfied everyone. Anderson himself expressed reservations about the completeness of the thermal model. The original analysis showed the acceleration was constant over a decade, while thermal radiation from decaying plutonium should diminish over time as the fuel degrades. The thermal model predicted a changing acceleration. The data showed a flat one. When Turishev's team reanalyzed with updated thermal models, they found a time-varying component, but the fit to the data required assumptions about the spacecraft's thermal properties that couldn't be independently verified. The original Pioneers are long dead. Pioneer 10 sent its last signal in 2003, Pioneer 11 in 1995. The raw tracking data from the critical early period exists in archived tapes at JPL, but a full independent reanalysis has never been conducted. Was the Pioneer anomaly really just waste heat? Why did the numerical coincidence with the Hubble constant arise if the cause was mundane? Why does the original constant acceleration data not match a decaying thermal source? And why was the thermal explanation accepted as definitive when the data fit required unverifiable assumptions about a dead spacecraft's heat distribution? The Pioneers are gone now, drifting silently through interstellar space, carrying golden plaques engraved with messages for anyone who might find them. The anomaly that once threatened to rewrite gravity is filed under solved, but solved and explained aren't always the same thing. And from spacecraft drifting off course, we move to a hole in the oldest light in the universe, a place where the Big Bang seems to be missing, the CMB cold spot. You're looking at a map of the entire sky painted in microwaves, the cosmic microwave background, that ancient afterglow of the Big Bang, and rendered in false color so human eyes can see temperature differences of millionths of a degree. Blues for slightly cooler regions, reds and yellows for slightly warmer ones. The whole map is remarkably uniform, almost perfectly smooth. The universe, at 380,000 years old, was an extraordinarily homogeneous place. Almost. Because in the southern sky, in the direction of the constellation Eridanus, there's a spot that's too cold, too large, too empty, and it shouldn't be there. The cold spot was first identified in 2004 by Patricio Vielva and colleagues at the University of Cantabria in Spain, using data from NASA's WMAP satellite. It's a region of the cosmic microwave background roughly 5 degrees across, about 10 times the diameter of the full moon on the sky, that is significantly colder than the surrounding CMB. The temperature deficit is approximately 70 microkelvins below the average. That sounds tiny. It is tiny in absolute terms. But in the context of the CMB, where temperature fluctuations are measured in millionths of a degree and the entire map is almost perfectly uniform, 70 microkelvins is enormous. It's like finding a dent in a billiard ball that's been polished to atomic smoothness. The CMB should not have a cold spot this large, this deep, or this sharp-edged. Its probability of occurring by chance in the standard cosmological model is roughly 1 to 2%. Unlikely, not impossible, but deeply uncomfortable for a model that's supposed to explain everything. What makes the cold spot genuinely strange isn't just the temperature, it's what's behind it. In 2007, Lawrence Rudnick and colleagues at the University of Minnesota cross-referenced the cold spot's position with galaxy surveys and found that the region corresponds to an enormous supervoid, a region of space roughly 1.8 billion light-years across, containing far fewer galaxies than expected. The CMB photons passing through this void would lose energy as the void expanded, arriving at our detectors slightly colder than photons that traveled through normal density regions. This is called the integrated Sachs-Wolf effect. It's real physics, and it could explain part of the cold spot's temperature deficit, but not all of it. Subsequent studies by Saputi and colleagues in 2015 confirmed the supervoid's existence using data from the Pan-STARRS and WISE surveys. The void is real. It's there. But thermal modeling shows it can only account for roughly 10 to 20% of the observed temperature deficit. The rest remains unexplained. The supervoid is too shallow and too close, at a redshift of about 0.22 corresponding to roughly 3 billion light-years, to produce the full cold signal through the integrated Sachs-Wolf effect alone. The mainstream position is that the cold spot is a statistical fluctuation. The CMB has many features. If you look at a complex enough map, you'll find outliers. The cold spot just happens to be the most extreme one in our particular sky. The supervoid contributes some cooling. The rest is cosmic variance, the random noise inherent in having only one universe to observe. It's unusual but not impossible. No new physics required. But Laura Mersini-Houghton, the same theoretical physicist from the University of North Carolina who proposed the multiverse explanation for the Buddha's void, offered a radically different interpretation. She proposed in 2007, before the supervoid was even confirmed, that the cold spot could be the imprint of quantum entanglement between our universe and an adjacent one. During the earliest moments of inflation, when our universe was exponentially expanding from a subatomic seed, it may have briefly interacted with a neighboring bubble universe. That interaction would have left a cold imprint on our CMB, a gravitational scar from the moment two universes touched. She predicted the cold spot's approximate size and temperature profile. The prediction matched the observations. She also predicted that a similar but smaller anomaly should exist in the opposite hemisphere of the sky. Some analyses have found a candidate signal, though it remains debated. Is the cold spot a statistical fluke that happened to align with a supervoid that can only explain a fraction of its temperature? Or is it something far stranger, a place where another universe pressed against ours 13.8 billion years ago, leaving behind a bruise in the oldest light that we can still see today? Why does the supervoid account for only a small fraction of the temperature deficit? Why did Mersini-Houghton's prediction match before the void was confirmed? And why is the most extraordinary possible explanation, contact with another universe, treated as fringe rather than as a testable hypothesis worth pursuing? From cold spots in ancient light, we move to something closer to home, something happening every time a spacecraft flies past our own planet that nobody can explain. The flyby anomaly. You're a mission controller at the European Space Agency. The year is 2005. The Rosetta spacecraft is executing a gravity assist maneuver around Earth, using our planet's gravitational field as a slingshot to gain speed for its long journey to Comet 67P. The math is precise. Orbital mechanics is one of the most exact sciences in existence. You know to the meter per second how fast Rosetta should be traveling after it whips around Earth. The maneuver completes. You check the tracking data. Rosetta is moving faster than it should be. Not by much. About 1.82 millimeters per second too fast. That's tiny, but it's real. It's outside the measurement error by a wide margin, and it's not the first time this has happened. The flyby anomaly was first documented by John Anderson, the same JPL researcher who identified the Pioneer anomaly. In 1990, NASA's Galileo spacecraft executed an Earth flyby on its way to Jupiter and gained approximately 3.92 millimeters per second, more than orbital mechanics predicted. In 1998, NASA's Near Shoemaker spacecraft flew past Earth and gained 13.46 millimeters per second, That's enormous by tracking standards. The Deep Space Network can measure spacecraft velocities to fractions of a millimeter per second. An unexplained surplus of 13.46 is screaming at you from the data. The pattern continued. Earth flybys by Cassini in 1999, Rosetta in 2005, and Messenger in 2005 all showed anomalous velocity changes. Some gained speed. Messenger actually lost a tiny amount. Anderson and colleagues published a comprehensive analysis in 2008 documenting the anomalies across multiple missions and proposing an empirical formula based on the spacecraft's incoming and outgoing trajectories relative to Earth's equator. The formula fit the data disturbingly well, but it had no physical basis. It described the pattern without explaining it. The list of rejected explanations is long. Atmospheric drag at the altitudes involved is negligible. Solar radiation pressure is accounted for in trajectory models. Tidal effects from the moon and sun are modeled precisely. Magnetic field interactions with spacecraft electronics have been calculated and found insufficient. General relativistic frame dragging effects are far too small. Earth's gravitational field is mapped in extraordinary detail by dedicated geodesy satellites. Every known force has been calculated, recalculated, and subtracted. The anomalous velocity changes persist. The mainstream response has been to treat the flyby anomaly as a probable systematic error in tracking data. Perhaps the Deep Space Network's Doppler measurements contain unmodeled atmospheric refraction effects. Perhaps thermal radiation from the spacecraft contributes in ways similar to the Pioneer anomaly explanation. In 2013, a European team proposed that the anomaly could be an artifact of how Earth's motion affects the timing of radio signals used for tracking. Some anomaly values have been reduced after refined modeling. ESA reported that the Rosetta flyby anomaly essentially disappeared after improved atmospheric modeling. But the 13.46 mm per second surplus from near Shoemaker has never been fully explained. Neither has the Galileo anomaly, and Anderson's empirical formula, which relates the anomaly to the spacecraft's trajectory relative to Earth's equatorial plane, has never been physically justified or definitively debunked. If the anomaly is purely a measurement artifact, why does it correlate with trajectory geometry? Measurement errors should be random, not systematic. Some physicists have proposed that the flyby anomaly could be evidence of an unknown interaction between rotating massive bodies and spacecraft, perhaps related to dark matter halos, modified gravity at planetary scales, or even frame dragging effects larger than general relativity predicts. Why do spacecraft gain unexplained speed during Earth flybys? Why does the anomaly correlate with trajectory geometry if it's just measurement error? What physical mechanism could Anderson's empirical formula be describing? And why has the anomaly been treated as resolved when the most dramatic cases remain unexplained? From spacecraft behaving strangely near Earth, we look outward to the far reaches of our solar system, where something massive is lurking in the dark, something so large it's warping the orbits of distant worlds, and we can't find it. Planet 9. You're Scott Shepard, an astronomer at the Carnegie Institution for Science. For years you've been cataloging the most distant objects in our solar system, tiny icy worlds orbiting far beyond Neptune in the Kuiper Belt and beyond. These objects are faint. They move slowly. Finding them requires patience, powerful telescopes, and years of careful observation. But you've noticed something wrong. The orbits aren't random. They're clustered. A group of the most distant known objects in the solar system. The bodies with orbits that take them thousands of years to complete a single loop around the Sun are all tilted and elongated in the same direction, as if something massive and invisible is hurting them, something out there in the dark. In 2016, Konstantin Batygin and Michael Brown at the California Institute of Technology published a paper in the Astronomical Journal that detonated across the scientific world. Using computer simulations of orbital mechanics, they demonstrated that the clustered orbits of 6 extreme trans-Neptunian objects could be explained by the gravitational influence of an undiscovered planet, a planet roughly 5 to 10 times the mass of Earth, orbiting the Sun at a distance of 400 to 800 astronomical units, completing one orbit every 10,000 to 20,000 years. They called it Planet 9. The evidence was circumstantial, but compelling. 6 objects with orbital periods exceeding 4,000 years all had their closest approaches to the Sun clustered within a narrow range of angles. The probability of this happening by chance was calculated at 0.007%, less than 1 in 10,000. Something was sculpting those orbits. Batygin and Brown's simulations showed that a single massive planet in the right orbit could explain not just the clustering, but also the existence of high-inclination Kuiper Belt objects tilted perpendicular to the plane of the solar system, objects that had previously defied explanation. The hunt began immediately. The world's most powerful telescopes pointed toward the predicted orbital zone, the Subaru telescope in Hawaii. the Dark Energy Survey Camera. The Vera Rubin Observatory when it comes online. Year after year, survey after survey, Planet 9 has not been found. Direct imaging has failed. No point of light matching the predicted brightness and motion has been detected despite multiple deep surveys of the most probable orbital regions. Skeptics have proposed that the orbital clustering is an observational bias. We find objects in the parts of the sky we look at. If surveys preferentially cover certain regions, the objects we discover will appear clustered even if the underlying population is random. In 2020, a study by Napier and colleagues argued that the clustering signal weakened substantially when observational biases were accounted for. The statistical significance of the clustering dropped. The evidence for Planet 9 became less compelling, but Badigian and Brown pushed back. They updated their analysis, incorporating new discoveries and refined bias corrections, and maintained the clustering was real. Additional lines of evidence accumulated. The slight tilt of the Sun's spin axis relative to the planetary plane could be explained by Planet 9's long-term gravitational influence. The peculiar orbits of certain centaurs, small bodies between Jupiter and Neptune, matched Planet 9 predictions. The theoretical case remained strong even as the observational search came up empty. Where is Planet 9? If it exists at the predicted mass and distance, why haven't the most powerful surveys on Earth found it? Could it be smaller and farther than predicted, lurking beyond current detection limits? Could the gravitational effects be caused by something other than a single planet? Perhaps a disk of small objects, a primordial black hole, or a rogue planet captured from interstellar space? Some researchers have seriously proposed that Planet 9 could be a primordial black hole the size of a baseball and with the mass of multiple Earths, essentially invisible to optical telescopes. If it's there, it would be the first new planet discovered in our solar system since Neptune in 1846. If it's not there, something else is sculpting those distant orbits and we don't know what. Either way, something is hiding at the edge of our solar system. And for missing planets, we turn to a missing element, because the Big Bang itself got its own chemistry wrong. The lithium problem. Rewind to the beginning, not the beginning of human history, the beginning of everything. The first 3 minutes after the Big Bang, the universe is a seething plasma of protons, neutrons, electrons, and photons. Temperature is in the billions of degrees. Nuclear reactions are raging. In this primordial furnace, the lightest elements are being forged. Hydrogen, helium, trace amounts of lithium. This process is called Big Bang nucleosynthesis, and it's one of the most precisely calculated predictions in all of cosmology. We know the physics, we know the temperatures, we know the densities. We can calculate exactly how much of each element the Big Bang should have produced. For hydrogen, the prediction matches observation perfectly. For helium, the match is exact. For lithium, the prediction is wrong, off by a factor of 3. Big Bang nucleosynthesis was first described in detail by Ralph Alpher, Hans Bethe, and George Gamow in 1948 in one of the most famous papers in cosmology, playfully authored as Alpha Beta Gamow, to echo Alpha Beta Gamma. Over the subsequent decades, the calculations were refined with increasingly precise nuclear physics data. The prediction for primordial lithium-7, the isotope produced in the early universe, is robust. It depends on the baryon-to-photon ratio, a fundamental cosmological parameter now precisely measured by the Planck satellite from CMB data. The calculation predicts roughly 3 times more lithium-7 than what's observed in the oldest, most primitive stars in our galaxy. These are stars that formed from nearly pristine Big Bang material, metal-poor halo stars that have been burning since the earliest epochs of the Milky Way. Their lithium abundances should reflect the primordial value. Instead, they consistently show about 1/3 of the predicted amount. The deficit is called the cosmological lithium problem, and it's been a thorn in the side of cosmology for over 3 decades. First identified clearly by Spite and Spite in 1982, it has only sharpened as measurements improved. The mainstream explanation appeals to stellar astrophysics. Perhaps the old stars have depleted their surface lithium over billions of years through mixing processes that carry lithium-rich surface material down into hotter interior layers where it's destroyed. This is plausible. Stars do process their surface elements, but the lithium abundances in the most primitive stars form a remarkably flat plateau, the Spite plateau, showing the same deficit regardless of temperature or metallicity. If stellar depletion were responsible, you'd expect variation. Hot stars and cool stars process lithium differently. The uniformity suggests the problem isn't the stars, it's the universe. Some physicists have proposed that the lithium problem points to new physics beyond the standard model. Exotic particles in the early universe, perhaps decaying supersymmetric particles or other relics from the first seconds after the Big Bang, could have altered the nuclear reaction networks in ways that destroyed lithium-7 after it formed. If the universe contained particles we haven't discovered yet, particles that interacted with nuclei during the first minutes of cosmic history, the lithium abundance could have been reduced to match observations. The lithium problem wouldn't be a problem at all. It would be a clue. Other proposals include variations in fundamental constants in the early universe. On non-standard cosmological models with different expansion rates during nucleosynthesis, and even primordial magnetic fields that altered reaction rates, none has gained consensus. The lithium problem persists, a factor of 3 discrepancy between the most precise prediction in cosmology and the most careful observations of the oldest stars. Why does the Big Bang's own chemistry fail for lithium when it succeeds perfectly for hydrogen and helium? Is the problem in the stars or in the physics of the early universe? Could the lithium deficit be evidence of new particles or forces that operated in the first minutes after the Big Bang? And why has a factor of 3 discrepancy in a foundational cosmological prediction been tolerated for over 40 years without resolution? The universe got its own recipe wrong. Or we got the recipe wrong, and from broken chemistry at the beginning of time. So we moved to a star that was supposed to explode for all the world to see, until someone quietly erased the prediction. KIC 9832227. You're Larry Molnar, an astronomer at Calvin University in Grand Rapids, Michigan. It's January 2017, and you've just held a press conference at the American Astronomical Society meeting that made international headlines. You've predicted that a specific binary star system, KIC 9832227, 2 stars spiraling into each other in the constellation Cygnus, will merge and explode in 2022, plus or minus about a year, producing a luminous red nova bright enough to see with the naked eye, a new star appearing in the sky. You've made the most specific astronomical prediction of the century. You've staked your career on it. Thousands of amateur astronomers mark their calendars. Journalists write feature articles. Documentary crews begin filming. And then you discover the whole thing was based on a typo. The prediction came from a pattern. In 2008, astronomer Romuald Thailenda analyzed the light curve of a contact binary star called V1309 Scorpii, and discovered that its orbital period had been accelerating exponentially in the years before it erupted as a luminous red nova in 2008. The 2 stars spiraled inward faster and faster until they merged in a violent explosion. Looking backward through archival data, Thailenda showed the exponential acceleration was visible for years before the merger. It was a signature, a predictive pattern. If you could identify another binary system showing the same exponential period decrease, you could predict the next merger. Molnar found one. KIC 9832222 Adia 7, a contact binary in the Kepler field, appeared to show exactly the same exponential decay in its orbital period. The curve fit beautifully. The acceleration matched the V1309 template. Extrapolating forward placed the merger in 2022. It was elegant. It was specific. Sabanyapa? It was the first time in history that a stellar explosion had been predicted in advance with a precise date. The media loved it. Science communicators hailed it as an example of how astronomy makes testable predictions. Molnar became a public figure. Observing programs were established to monitor the star in real time. Everything was in place for the most anticipated celestial event in living memory. Then, in September 2018, Molnar published a retraction. A colleague, Quentin Socia at San Diego State University, had gone back to the original data and discovered that one of the key timing measurements from a 2008 paper by Kinamuchi and colleagues contained an error. A single data point in the period analysis had an incorrect timestamp. It was off by 12 hours, the difference between a full day and a half day in the binary's orbital cycle. When that single data point was corrected, the exponential curve collapsed. The orbital period of KIC 9832227 wasn't accelerating toward merger. It was fluctuating normally. There would be no new star in 2022. The prediction was dead. Molnar, to his credit, published the retraction openly and framed it as a lesson in the scientific method. Predictions must be tested. Errors must be corrected. Science works. The media covered the retraction far less than the original prediction. The story quietly faded. A few articles noted the correction. Most of the public never learned the explosion wasn't happening. The documentary footage was shelved. The calendar reminders expired unnoticed. But the deeper question went unasked. How did a single timing error in an archival data point survive peer review, multiple analyses, and years of scrutiny by professional astronomers before being caught? How many other predictions in stellar astrophysics rest on similarly fragile data foundations? And what does it say about the incentive structure of modern science that a dramatic, media-friendly prediction received vastly more attention and resources than the quiet, careful verification work that ultimately debunked it? The correction required someone going back to primary sources and checking a number. It took years for anyone to bother. When science celebrates the prediction but buries the retraction, what patterns are we missing? How many other confident announcements rest on a single data point that nobody's checked? And what would have happened to Molnar's career if the error hadn't been found until 2022, when the sky remained stubbornly dark? From predictions that vanished, we turn to a signal from the collision of two black holes that shouldn't exist, because the universe made something the standard model says is impossible. GW1 90521, September 2020. The LIGO and Virgo gravitational wave observatories announced the detection of a signal from May 21st, 2019. Two black holes collided and merged roughly 5 billion years ago, sending ripples through space-time that reached Earth as a faint chirp lasting a fraction of a second. Gravitational wave detections are no longer new by this point. LIGO made the first detection in 2015. Dozens have followed. But this one is different. The two black holes that merged had masses of approximately 85 and 66 solar masses. Their merger produced a final black hole of about 142 solar masses, with the remaining 9 solar masses radiated away as pure gravitational energy. The problem is the 85 solar mass black hole. According to stellar physics, it shouldn't exist. Stars produce black holes when they die. When a massive star exhausts its nuclear fuel, its core collapses. If the star is heavy enough, nothing stops the collapse and a black hole forms. But there's a gap. Stars between roughly 65 and 130 solar masses don't form black holes when they die. They blow themselves apart completely in a process called pair instability supernovae. At those masses, the core becomes so hot that photons spontaneously convert into electron-positron pairs, robbing the core of radiation pressure. The star becomes dynamically unstable and detonates entirely, leaving nothing behind, no remnant, no black hole. And just an expanding cloud of debris. This means black holes formed from stellar collapse should come in two flavors, those below about 65 solar masses and those above about 130 solar masses. The region in between, the pair instability mass gap, should be empty. No stellar process can create a black hole in that range. The 85 solar mass component of GW1 9052. 1 sits squarely inside the gap. It shouldn't exist, and yet the gravitational wave signal is clear. Two objects with those masses merged. The signal matches general relativity's predictions for such a merger with extraordinary precision. The data isn't ambiguous. Something created an 85 solar mass black hole through a process that current stellar physics says is impossible. The mainstream response has been to propose hierarchical mergers. Perhaps the 85 solar mass black hole was itself the product of a previous merger between two smaller black holes, each below the pair instability gap, that combined in a dense stellar environment like a globular cluster's core. This is physically plausible. Dense stellar environments do produce repeated mergers, but the spin of the final black hole in GW19052I1 doesn't match the predictions of hierarchical merger models particularly well. The signal is also so short, just 4 gravitational wave cycles in the detector's sensitive band, that alternative interpretations have been proposed, including the possibility that it wasn't a binary black hole merger at all, but rather an eccentric encounter, or even the collapse of a rotating massive star. Other theorists have proposed that the 85 solar mass black hole formed from a star in a low metallicity environment, where pair instability physics operates differently, potentially allowing some massive stars to collapse directly into black holes without detonating. This would require revising the pair instability threshold, which is currently well supported by nuclear physics calculations. Still others suggest it could be a primordial black hole, formed not from a star at all, but from density fluctuations in the early universe fractions of a second after the Big Bang. Primordial black holes don't obey stellar mass limits because they weren't made by stars. Each explanation works partially. None works completely. The pair instability mass gap was one of the cleanest predictions in stellar astrophysics. GW190521 punched a hole in it, and the response has been to patch the theory rather than question whether the theory was complete. What created a black hole in the forbidden mass range? Is our understanding of pair instability supernovae incomplete? Could primordial black holes from the earliest moments of the universe be merging in the present day? And if the cleanest prediction in stellar death is wrong, what else have we gotten wrong about how stars live and die? From impossible black holes, we descend to the bottom of the world, where a detector buried in Antarctic ice has found particles doing something that violates the known laws of physics. The Anita events. Antarctica. A helium balloon the size of a football stadium floats 23 miles above the ice sheet, carrying an array of radio antennas pointed downward. This is ANITA, the Antarctic Impulsive Transient Antenna, designed to detect ultra-high energy cosmic neutrinos. When a neutrino from deep space strikes an atom in the Antarctic ice, it produces a cascade of particles that emits a burst of radio waves. ANITA listens for those radio bursts from above, scanning millions of square kilometers of ice below. In 2006 and again in 2014, ANITA detected something it wasn't supposed to. Radio signals coming not from above, where cosmic rays and neutrinos arrive from space, but from below, from inside the Earth. It's ice signals that appeared to show ultra-high energy particles emerging upward through the planet. Here's why that's impossible. Ultra-high energy neutrinos, the kind with energies above 10 to the 18th electron volts, interact with matter. At those energies, neutrinos can't pass through the entire Earth. The planet is opaque to them. They'd be absorbed long before reaching the other side. Low-energy neutrinos pass through the Earth effortlessly. Trillions of them are streaming through your body right now without interacting. But at the energies ANITA detected, approximately 0.6 exaelectron volts, the cross-section for interaction with matter is too large. The particles should have been absorbed by thousands of kilometers of rock before reaching Antarctic ice. The ANITA collaboration, led by Peter Gorham at the University of Hawaii, published the anomalous events and noted they defied explanation within the standard model of particle physics. Two events detected in separate flights years apart showed particles arriving from steep angles below the horizon, having apparently traversed hundreds of kilometers of Earth at energies where the planet should be a solid wall. The signals looked like tau neutrinos emerging from the ice after converting to tau leptons, which then decayed and produced the radio burst ANITA detected. But no known particle at those energies should have made the trip. The events triggered a wave of theoretical papers. Some physicists proposed that the ANITA signals were evidence of supersymmetric particles, tau-slepton, a heavy superpartner of the tau lepton that could traverse the Earth more easily than standard model neutrinos. Others suggested sterile neutrinos, hypothetical particles that interact only through gravity and could pass through matter unimpeded before converting to detectable particles near the surface. Some proposed even more exotic explanations. Decaying dark matter, cosmic strings, magnetic monopoles. The mainstream response has been cautious. The IceCube Neutrino Observatory, a cubic kilometer detector buried in Antarctic ice near the South Pole, searched for corresponding signals and found none. If a new type of particle were regularly punching through the Earth, IceCube should have seen a population of similar events. The absence of IceCube confirmation led some researchers to argue the ANITA events were likely misidentified reflected cosmic ray signals, ordinary particles bouncing off subsurface features in the ice rather than emerging through the Earth. But the ANITA collaboration's analysis specifically tested for reflected signals and found the events were inconsistent with reflection. The polarity of the radio signals was inverted compared to what reflection would produce. The geometry of the detection didn't match surface or subsurface bouncing. Gorham and colleagues maintained the events were genuinely anomalous, not instrumental artifacts and not reflections. The debate remains unresolved. The ANITA events have never been reproduced or confirmed by independent detectors. They haven't been definitively explained within the standard model, and they haven't been definitively debunked. They sit in a scientific gray zone, too anomalous to ignore, too isolated to build a theory on. The kind of data that gets mentioned in review papers but not in textbooks. What came through the Earth in 2006 and 2014? If it wasn't a standard model particle, what was it? Why did IceCube see nothing similar? And if the events are real, are they the first evidence of physics beyond the standard model detected not in a particle accelerator, but in a block of Antarctic ice? From particles that shouldn't exist, we turn to a star that shouldn't exist either, because it appears to be older than the universe itself. The Methuselah star. You're an astronomer studying HD 140283, an ancient, metal-poor subgiant star, roughly 190 light-years from Earth in the constellation Libra. It's a well-studied star, catalogued for over a century, unremarkable in appearance. But when you calculate its age using well-established stellar evolution models, the number that comes back is 14.46 billion years, plus or minus 800 million years. The universe itself is 13.8 billion years old. This star, sitting quietly in our galactic neighborhood, appears to be 600 million years older than everything that exists. HD 140283, informally called the Methuselah star, has been the subject of age estimates since the 1990s. The star's extreme age became a prominent issue in 2013 when Howard Bond and colleagues at Penn State University published a refined age estimate using the Hubble Space Telescope's fine guidance sensors to measure the star's parallax with unprecedented precision. Their result was 14.46 billion years, with a formal uncertainty of plus or minus 800 million. The error bar is critical. It means the star's age is statistically consistent with 13.66 billion years at the lower end, just barely younger than the universe. But the best fit value, the number the models produce when you plug in all the measurements, places the star before the Big Bang. The measurements feeding the age calculation are solid. Hubble's parallax measurement gives a precise distance, which gives a precise luminosity. Spectroscopic analysis gives the star's chemical composition extremely low in heavy elements, consistent with formation in the early universe. Stellar evolution models then use these inputs to compute how old the star must be based on its current temperature, brightness, and evolutionary stage. Every input is well measured, the models are well tested, and the answer is impossible. The mainstream resolution focuses on the error bars. At 800 million years of uncertainty, the star could be 13.66 billion years old, comfortably younger than the universe. The central value of 14.46 billion years is just a statistical artifact. Push it down by 1 sigma and the paradox disappears. Additionally, updated nuclear reaction rates, particularly the rate at which carbon-14 is produced in stellar interiors, could shift the age estimate downward. Revised oxygen abundance measurements published after Bond's paper suggested the star might be slightly younger than the initial calculation. The paradox, according to the mainstream view, is an artifact of measurement precision, not a real conflict. But 1 sigma isn't very much. In scientific terms, 1 sigma means there's roughly a 32% chance the true value lies outside that range. The probability that the star is older than 13.8 billion years. Shia, based on the published measurements and error bars, isn't negligible. It's not 1 in a million. It's not 1 in 1,000. It's a substantial percentage. And while revised nuclear rates and oxygen abundances push the age down slightly, they don't eliminate the tension entirely. The star remains among the oldest known objects in the galaxy, and its age estimate keeps brushing uncomfortably close to, and sometimes exceeding, the age of the cosmos. Other ultra-metal-poor stars show similar tensions. Several stars in the galactic halo and in globular clusters yield age estimates that crowd the age of the universe or exceed it depending on which stellar models and nuclear physics inputs are used. HD 1-40283 is the most famous example, but it's not alone. The problem recurs across the oldest stellar populations. Is the age of the universe precisely right? The 13.8 billion year figure comes from the Planck satellite's measurement of the cosmic microwave background. It's the most precise cosmological measurement ever made, but it assumes a specific cosmological model, lambda CDM, with specific values for the Hubble constant, dark energy density, and dark matter density. If any of those parameters are slightly off, the age of the universe shifts, and there is currently an unresolved tension in the measured value of the Hubble constant, the rate at which the universe is expanding. Different methods give different answers. A discrepancy known as the Hubble tension. If the Hubble constant is higher than the Planck value, the universe is younger, making the Methuselah star even more impossible. If it's lower, the universe is older, and the tension eases. How old is HD 1-40283, really? Why do the best fit models consistently produce an age older than the universe? Is the problem in the star, in the stellar models, or in our measurement of the age of the cosmos? And what does it mean if multiple independent methods keep producing stars that appear older than everything? From a star older than time, we reach the question that all of these discoveries have been building toward: the Great Silence. You've now seen spacecraft drifting in directions physics can't explain, a cold spot in the oldest light that might be a scar from another universe, particles emerging through the solid Earth in violation of the Standard Model, a star that appears to have existed before the Big Bang, black holes in mass ranges that stellar physics says are impossible, a missing element the universe forgot to make, a planet sculpting orbits from the shadows that no telescope can find, a stellar explosion prediction built on a single unchecked number, and spacecraft gaining unexplained energy every time they swing past our own planet. Each one of these discoveries was real, measured by instruments, published in journals, confirmed by independent analysis, and each one was quietly filed away. Not debunked, filed, downgraded from discovery to anomaly, from anomaly to edge case, from edge case to footnote, the pioneer anomaly, resolved by thermal modeling that doesn't perfectly fit the data, the CMB cold spot, a statistical fluke that happens to align with a supervoid that can't explain it, the flyby anomaly, probably measurement error except when it isn't, Planet 9, probably real except we can't find it, the lithium problem, probably stellar physics except the Spite Plateau says otherwise, KIC 9832227, a prediction built on a number nobody checked for years. GW1 90521, a black hole that broke a clean prediction, patched with hierarchical mergers that don't quite fit. The Anita events, anomalous particles that haven't been confirmed or explained. The Methuselah star, older than the universe unless you push the error bars just right. The pattern isn't that these discoveries are wrong. The pattern is that they're uncomfortable, each one tugs at a different thread. General relativity, the Standard Model, Big Bang nucleosynthesis, stellar evolution, the age of the cosmos, the structure of space-time. Pull any single thread and the fabric holds. It stretches, it accommodates, but pull all of them at once and something gives. Science doesn't progress by ignoring what it can't explain. It progresses by staring at the things that don't fit until new understanding emerges. The ultraviolet catastrophe didn't make sense until quantum mechanics was born. The precession of Mercury's orbit was a footnote until Einstein turned it into proof of general relativity. Anomalies aren't embarrassments, they're invitations. But invitations require someone willing to walk through the door. And in modern science, where funding follows consensus and careers are built on incremental progress within established frameworks, walking through that door carries risk. The physicist who proposes that the pioneer anomaly reveals new gravity risks being dismissed as a crank. The astronomer who suggests the Anita events signal new particles risks losing grants. The cosmologist who questions whether the universe's age is precisely known risks their standing in a field built on that number. The anomalies don't go away. They accumulate. They sit in the data like stones in a pocket, each one too small to notice individually, but together heavy enough to drag you under. Spacecraft drift. Ancient light has holes. Elements are missing. Stars are too old. Black holes break the rules. Particles defy the laws. And the response every single time is the same. Reclassify, reframe, downgrade, move on. 10 discoveries, 10 comfortable explanations, and 10 cases where the data is still sitting there, waiting for someone brave enough to ask what it actually means. The universe isn't hiding its secrets. It's putting them right in front of us. The question isn't whether the evidence exists. It does. The question is whether we have the courage to follow it, or whether we'll keep doing what we've always done, filing it away, calling it resolved, and pretending the silence is empty when it's full of answers we're afraid to hear.